Well, good afternoon, everyone. I'm Mackenzie Ross with OneSpin. Thank you for joining us today. It's really great to see a lot of, I think, not super food coma faces from lunch. You've had a little bit of time at least to kind of get going, but it's really a pleasure to see all of you here. Today we're going to be talking a little bit about using mutation coverage for advanced bug hunting, and also some other stuff that maybe doesn't necessarily fall under that title's umbrella, but it should be great. So without further ado, I'd like to introduce our Director of Application Engineering, Vladislav Palfy. And later on, you're going to be hearing from Nicolae Tusinschi, who is our Product Specialist for Design Verification. Would you guys rather hold all questions to the end? Do you want people to jump in?
Maybe end is better.
Okay.
It's a big crowd.
Yeah. So I guess in the interest of time, please hold all questions to the end. But if you do think of something, feel free to tweet us if you would like to. Our social media team is here, so we'll be monitoring that along the way. We're at OneSpin Solution. Okay? Vladislav, it's up to you.
Okay. Hi for the first time. It's lovely to see you in such big numbers, so let's get started, shall we? I will be taking you through the first part of the presentation of using mutation coverage for advanced bug hunting. And I want to start with something that we are all familiar with by introducing the standard verification loop. So namely, this is what we all do. We go from requirements, we derive a verification plan, we build our test benches, then we run some debug, and if everything's okay, we can get to sign off. And this is what people are used to doing, but we want to approach this from a formal perspective and see how this can be done using formal verification. So the first thing I want to talk about is assessing the quality of verification. If you don't measure, you actually don't know. So what we want to achieve here is actually answer some questions like what we should exactly be measuring, and how do we get this data in a user-friendly, readable way presented to the users so that it can actually aid your verification effort. And there are also some, you can say, philosophical questions that you could ask is like, when am I done with my verification? So you want to make sure that you answer the questions like, have I written enough stimuli, or which parts of the design have actually been exercised by my test benches? How good the quality of my checks is, that's a big question we have to answer. And also which parts of the design are actually checked by my checkers. All of these questions we can answer by what I'm going to talk about today, together with Nicolae, which is our observation coverage solution called Quantify. And we have additional two questions listed here, which we're not going to go into today, but when it comes to specified functions and whether they're all verified, OneSpin has a different solution called gap-free, so this is not the topic for today, but you're welcome to come to us and we can discuss this as well at some point. But for now, let's stick to coverage. So when it comes to coverage and bug hunting, we see it as two sides of one coin. And I think this is a question that hasn't been answered so far because usually people keep it as separate topics. And we want to show you the way that you could actually look at bug hunting and coverage in a unified way. We can all agree that both are equally important, bug hunting and coverage. And while as coverage is a way to measure and to analyze your design, bugs are more anecdotal in the sense that you're not really sure when you come across one, but you definitely want to get rid of all of them. And if you would say that you have 100% coverage and you still have bugs in the code, then that coverage is really not of much value to you. And these are some of the questions we're going to target today. And of course, extracting this coverage should be fast, should be easy, and it should be in a format which actually helps you do your bug hunting and guide your verification effort, and it should be human readable. So at this point, let me explain what we mean by quantify and what we mean by observation coverage. So if you look at here, we have sort of a been there, done that approach. If you look at the left side, this is what you're maybe used to in simulation. You have to check how many statements in your design you can actually activate, and you're actually checking the quality of your stimuli. In simulation, you would do this by writing test benches, maybe doing constrained random to capture as much as possible. In formal verification, the stimuli comes for free. So the formal engines are able to extract all possible input combinations and drive your design with those. So you might be wondering why you need to worry about the quality, and it is because in formal verification, you might want to constrain out some illegal behavior, because you get 100%, and not all of the 100% is something you want to drive your design. when you are doing constraining, it is highly possible that you will do over-constraints. Right? So you might accidentally switch off some functionality in your design, which can then mask bugs. So the first question we ask is, how good of a quality is our stimuli? Then on the right side, this is what we introduce. We do observation coverage, and here we actually ask the questions, if a statement has been activated, are the checkers we have sensitive to this statement? So we are actually able to measure the quality of our checkers. And the way we do that, if the pointer works, if I can point, oh no, it doesn't, okay. So if you look here where it says modify, what we actually do is we introduce a free variable to every assignment, which allows us to model different kinds of mutations, basically, right? So we cover all possible mutations on all possible assignments, and this can unearth some interesting scenarios. And the question we are trying to answer here is, if this specific line does something different than it usually should do, would there be an assertion that would now start failing? Meaning that the actual checker or the assertion is sensitive to the functionality of this line of code. And that's when we say the actual checker covers that particular line of code. So this is a powerful technology, which is, I think, the most complete mutation model on the market for formal, and it has been a OneSpin patent for a decade now almost. So going further into quantify, basically what you want to do is you want to take an input, which is your design and your assertion set, and you want to be very quick and with a push of a button get some metrics which are human readable and meaningful to you as a user. And we can actually dive into the other points a bit later, but the way we propose that this is used is, if you remember the first slide where we talked about the usual flow, we believe that coverage should not be left until the end, and it's not something that you do at the end of your verification flow necessarily, but you can have an iterative flow where you can have designers using this coverage solution as well to unearth bugs. And if I give you one example, since this is formal verification, you get all the input stimuli for free. Even if your designer doesn't do any verification at all, he could still run quantify on his code without any checks, and it will be able to identify whether he has some dead code, for example, or whether there is redundant code. So if you're, for example, doing some area optimizations, you want to get rid of any redundancy, quantify is the way to go. And then later on, these results can be reused by the verification people, and we are achieving what formal anyway does, is a shift left in verification effort, so you unearth more bugs earlier in your design verification cycle. So this is the idea behind it. And if we talk about designers, right, so let's say if you have your designers doing nothing but design, you still can have a designer bring up view. As I mentioned just before, you can still have dead code and reachability checks running. You can identify redundant code. So it's still valuable information, and it can still unearth some bugs in the design that you don't later have to capture with complex test benches and waste valuable verification time. So designers can get rid of this quickly. And if you have designers that maybe run some inline assertions as well, even better, because you can already quantify these assertions and start verifying your code even during the design cycle. And in case you're a verification engineer, well then, your job is slightly different. The designer might not care for every possible scenario, right? They just want to test as they design whether what they designed makes sense. As a verification engineer, you'll probably try to break the design, right? Because that's your job. And to do that, you need to write a lot of assertions, a lot of checkers, cover statements, assumptions. And what we try to provide to you with quantify as a metric is an indication where your verification gaps are. And so whether you have some checks that are missing, we can guide your verification to tell you which checks you should be writing next. We can identify over-constraining, meaning that your constraints are maybe masking some bugs or limiting the functionality of your design. And in the end, of course, we can find bugs is what verification people should be doing. So coming into the way we report this, we already spoke about control on the left side, if you remember the quality of the stimuli. So from the controllability side, we can have different results. For example, we can have dead code identified. And again, this being formal verification, when code is reported as dead code, that means that there is absolutely no input trace that can activate this line of code. So unlike simulation, this is real dead code, and there is nothing you can do to run that line of code. We also identified code which is reached, and note that we say reached and not reachable, because this is actually reached by an assertion you wrote, so our line of code can be activated. And we can identify code which is constrained, which is basically the same as dead code, but it's not dead by design, it's dead due to a constraint that you introduced. And by reviewing this, you can actually measure the quality for constraints and make sure that you're not over-constrained. Why is this important? Because if something is unreachable, you cannot control it, and if you cannot control it, you cannot observe it, so your checks are completely useless on this portion of code, and that's valuable information to have. If we move to the observability side of things, there we can have something which is what we call uncovered, meaning not observed. So you can still have plenty of assertions written, and it can still happen that some lines of code are not even activated, in which case they will be reported as uncovered. In case you reach a line of code, but there is no check which is sensitive to it, we will report it as unobserved, which means reached but not observed. And the result you actually want to have is covered, meaning that the line of code has been exercised and there is an assertion which is sensitive to what that line of code does, meaning that it's also covered in a functional manner. And last but not least, as mentioned before, we can also identify code which is redundant, can be valuable information for designers. We identify code which is just verification code, which is not interesting for the actual verification, so we can roll it out. And we also allow users to exclude some pieces of code from quantification if they wish so. Maybe you have something already covered by simulation, you don't want to waste computing time here, so you can just tell quantify, don't focus on this. And this is then the complete overview, and what we will focus in the second part of the presentation is the verification code. Right? So the code that is dead, that is constrained, that is uncovered, and that is reached but not observed by an assertion. This is what we will use to hunt bugs in our code throughout the design and verification cycle. Now, before we do that, I just want to talk about the quantified dashboard and how we report these results. So this is the high-level overview, and as you can see, all the results that I explained on the previous slides are there. And our customers find this handy as a sort of management point of view of the verification effort that has been performed so far. So in this case, we have 80% of the code covered and 20% uncovered. So let's say a manager passes by Friday morning through all the reports, he will know exactly which engineer has made which amount of progress. And we also report redundant code, as mentioned. And we have the functional results here. So these are all the checkers that you're using, all the assertions and their results. So this is now the functional part of the coverage, so assertion result coverage also reported in this dashboard. Now if you're a, say, manager, this will be enough for you. You can skim through the results, you can see who is where, and hopefully, make a round of golf, because it's easy to see and easy to understand. If you're a verification engineer though, what you could do is you can dig deeper in the code. So by clicking on the source code, you can unveil your source code, and this is how we annotate the result. Right? So in this small example, we have code which is verified, meaning that it's covered by an assertion, so that's where you're good. That's where you have a checker which is verifying the specific line of code. You can have a verification call. In this case, this code hasn't even been exercised, so this might be a portion of code you want to concentrate on with your next checker. We can have code which is constrained, meaning that you have some system error like a SU, which prevents this code from being executed. And in the end, in black, we have some dead code, which is dead by design, and there is no way you can reach it unless you change the design itself. Okay, so at this point, we could start talking about quantify in action. And I will be talking about the small FIFO example that we have, and then my colleague will talk about his results on a bigger, more real-world design. But to illustrate the point, we're going to use a design we all know and love, which is a FIFO. Some people love it more than others, Ashish, right? So we want to make sure that our FIFO, which has a write and read handshake, is outputting the data correctly, so we don't want any reordering, we don't want data duplication, and we don't want drop packets. So the same way you would normally go about verifying anything, we will start with some requirements. So you might have a verification plan in place, you might not, this is a small design. But regardless, we can make some statements of what we want to prove the design does. Right? So we already said ordering is correct, no duplication, no lost data, no data corruption, and we probably want to do some checks whether the FIFO is empty and full. Right? So that it can be empty and full at the right time, and that it can get full and drained and filled back. So let's say we run quantify with no checks at all, which is possible. Unfortunately, this design doesn't have that code, but this is something that the designer might be doing, right? He said, okay, here's my design, I'm going to quantify it at least for that redundant code. I'm not expecting anything else to happen because I don't have a checker. And as expected, this is all because there's no that code, this is all uncovered, we don't have any checkers, so we don't generate any stimuli, nothing is reached. But if we start implementing some checks, let's say we talk about an order check, and I'm just going to quickly introduce some basic abstraction here. So what we're going to do here is we're going to take two values, which can be any value at all. They're just used as samples. And I want to make sure that I sample data 1 and data 2, and that they exit the FIFO in the same order. And for this, I can write an ordering check. It's actually very simple. I'm going to say that if data 1 wasn't sampled in, data 2 wasn't sampled in as well. That's my assumption. And then my ordering check is going to say that if I have sampled data 1 and data 2, and data 1 is not out yet, data 2 isn't out as well. So this just makes sure that they enter and exit the FIFO in the same order. And the data value, since it's formal, can be arbitrary, right? So the tool will take care of all the possible values. Okay, so I've written my ordering check, and I'm expecting pretty high coverage. It's a FIFO, right? So it should be simple. So let's see what quantify says. And quantify says that we did cover 63% of the design, but a third of the design is still unobserved. And if we zoom into the source code a bit, it's very easy to see where the coverage is missing, so you just follow the red and the yellow. So we have some unobserved code in yellow, which means that our ordering check stimuli has been able to fire this line of code, so it's reached, but it doesn't observe it, so it doesn't really prove anything about this code. And we even have some code which was not exercised at all. So I don't know how visible it is, but it's very easy to see that empty and full are unverified, so we didn't actually write any check about the FIFO being empty or being full. So we can add these checks next. So we add three properties. So the first one is empty to full, where we say that if the FIFO is empty and we do pushes without pops for the depth of the FIFO, it's going to be flagged as full. Empty is the same, just the other way around. And we actually add one assertion which says that the FIFO is empty after reset. So let's quantify this again. How are we doing now? So actually the coverage has increased. We have 72%. Maybe not as much as we expected. But what is worse is we now have a check which is failing. And it's vacuous, meaning that it's not being executed. And the check name is empty. So we now reveal that our FIFO actually cannot get empty at all. And if we again zoom in on the code, we cannot observe empty still. And quantify is not telling you which part of the code you should look at next. Because we cannot observe empty, we want to zoom in on this. And if I do zoom in, well, there is a design error here. Maybe an awkward way to design it, but for illustration purposes, we actually said if the FIFO is empty, then don't read from it. But if it's not empty, we said also don't write it. So it's a bit opposite than what we wanted to do. And if you fix this bug, run quantify again, we're now at 77%, but we are still missing the 22%. So some people would say, okay, my checks are holding now, the coverage is not that bad, maybe I can sign off. But since quantify is giving you observability of your code and whether the checks are really checking your lines of code, you still cannot sign off. You still need to dig deeper. And in this case, we are missing coverage now on the right handshake. Now you might say because we have the ordering check and because we've shown the FIFO can get full, obviously there is a right handshake happening, otherwise we wouldn't have anything going into the FIFO. But quantify is still telling us this is not observed, so something is wrong. And it forces us to think a little bit more of which checks are maybe needed to cover this behavior. And since we didn't talk about any deadlock checks, we might want to add some liveness constraints, which are saying that, liveness checks, which are saying that the right handshake and the read handshake will eventually happen. And if we use liveness, we need fairness constraints, which said that they will happen at some point. Okay, so when we add these checks, let's see where we are now. Okay, so now the design coverage is at 90%. And at this stage, I can almost bet that most of people would say, okay, 90%, I've done all my checks are green, they all hold, they're proven against the design, 90%, a pretty high number, I'm ready to sign off. So can I have a show of hands who has signed off with 90% of coverage before? Come on, be honest, it can't be only one. Okay. For those of you in the front row, everybody puts their hands back. Just so you know. Right, so at this stage, if we didn't have quantify, we would most certainly sign off because we've done enough checks, we don't have any vacuous proofs, all our assumptions are okay, we don't have over-constraining, it's a very high metric. But since, again, this is observation coverage, you really should look into what it's telling you. And what it is telling us in this case is that there is still some yellow part on the handshake, on the FIFO being full. So if we zoom into this code, let's see what we have. So if you look at the full flag of the FIFO, we are saying that if the FIFO is full, the right acknowledge should be 0. But actually the right acknowledge will be 0 in the next cycle, in this case. So what we're actually allowing to do is to write to the FIFO in the very last cycle. When it becomes full, we can still write one element to it. And then we can ask questions, why didn't the order check fail, right? Because obviously we can overwrite the last element in the FIFO once in the same cycle once it gets full. So how come the order check is saying that everything is okay? So at this point, you might want to think, where else are you mentioning this particular signal, the right acknowledge? And if we review our design, we are actually mentioning it in a constraint. And we do this in a constraint that says, if the FIFO is full, there will be no write or there will be a read. So what this constraint does is it actually forces a read whenever the FIFO gets full. And it's actually masking the bug that the last element of the FIFO is being rewritten. And without quantify telling you that pieces of code are unobserved, probably you wouldn't think about this. And so this is how it's guiding you towards looking at the important pieces of code. So if I remove this constraint, which is obviously over-constraining the functionality of my design, well, guess what? We now have 2 checks failing. So the order check now starts to fail. And if you look at the debug of this check, you can see that when the FIFO is full, there is still one write asserted, and that the value 1 is overwriting the value 0 there. Okay, so let's quantify this again with this assertion set. And if we do, well, guess what? We were comfortably at 90%, ready to pack up and go home, and boom, we're back at 63. Right? So it's not that easy as it seems. Of course, we have no proofs for these 2 assertions. We need to fix them. And to do that, we need to model this write and read acknowledges properly. And once we do this, fix the bug and quantify again, now we have 100% covered. Right, so now we don't have design bugs, we have no over constraints, all the design statements are covered, And this is now a metric which allows you to say that you are in fact done with verification. Right? So now you can be ready to sign off. And the question is, what happened to our constraints? Well, actually the design is designed in such a way that the constraints are not required anymore. So it's acting like it's acting due to the design. But you can still check whether this is true. So what you can do is you can add more checks, which were before constraints, and actually prove them against the design. So you prove that the design is actually doing what it's supposed to be doing. This will not decrease your coverage, which is already 100%, but it's a good check to have. Okay, so let's recap before I hand it over to my colleague. So, what did we do? We showed that without the test bench, everything is uncovered. Then we added an ordinary check, which got us to 63%. We followed the verification holes indicated by the HTML view of quantify and added missing checks for empty and full. Then we realized that the FIFO doesn't get empty, so we use quantify to target a piece of code and unearth a bug. We fixed that bug, quantified again, we still had unobserved statements. And then we added some more checks, and we finally got to the point where we needed to release our constraint because we were over-constraining our design, which was masking another bug. Okay, and if you do have bugs in the design, it's very obvious you don't have 100% coverage. So what quantify is able to do for you is it can force you to think about the checks you're missing. It can force you to think about the environment you created using the constraints, whether you're over-constrained or not. It can guide your verification effort and give you a clear metric of how far down the road are you with your verification. And overall, what we do with quantify and what we have our customers doing is that we find bugs, we remove bad constraints, and we guide you to 100% verification coverage. And we highly advise that you start using this coverage sooner, as soon as you start reading your design the first time in an iterative manner, because it can help you get rid of bugs early in the design cycle, which is much less expensive than finding them before tape-out. So that was the first part from me, and now I would like to hand over to Nicolae, who is going to talk about something a tad more complicated than a FIFO, and how he used quantify to verify a serial protocol.
Good afternoon. Do you hear me well? Yeah? Okay, good. So, starting from the beginning. So, the topic of this discussion I'm going to carry on is not about how to verify the I2C serial protocol with using formal. It's about how coverage, using coverage results given by quantify, gives you it is the role of coverage in when you have to verify such a design. Yeah, and moving on, so so in a systematic verification flow, for example, everything starts from a requirement that is broken into individual features and sub-features, and for each sub-feature there is a verification goal. And it's the decision of the verification engineer what kind of verification he should apply. And it can go to direct test, to formal, etc., etc. And assertion-based verification, assertion-based formal verification is ideal for this task. And as you see in the graph, so everything starts from requirements, ends up in a verification plan. From there, an engineer, he or she decides is this part going to be verified by simulation, or this part of the design is going to be verified with formal. At the end of the day, everything ends up in some coverage results, simulation coverage results or formal coverage results, and they go back into common database, which then brings me to this new view. And as I mentioned before, starting from requirements, everything gets into a spec. From this spec, a verification plan, which is not annotated, is derived. Then the engineer decides it goes for simulation or formal, or both. And at the end of the day, the simulation results and formal results are merged into a common database. which are fed back into the verification plan, getting annotated, and then are ready to for sign-off. Coming back to the case study we carried in OneSpin, so the main motivation for this was to get to bring and to leverage the coverage results from Quantify in your verification process for it. And we decided to use an I2C design, which is a master one, presented master functionality. And and so mainly two challenges were here. Like, first would be like, how can coverage assist you in your verification process? And second, like, it was to how can we verify serial protocols using formal? Because even slow SOCs today are running at higher frequency, higher clock frequencies, and the standard mode in I2C is up to 100 kilohertz. So if you do the math, formal tool needs to prove it needs to check for many cycles in order to prove that a single byte is transferred correctly. What would be an ideal approach to verify such an I2C design or serial protocol? Because first of all, you have to verify that it's protocol compliant, and after that you have to verify that the data doesn't get corrupted or there is data loss. Yeah, so these were our two main goals for this case study, and I'm not going to talk about a lot about I2C, just to introduce you what is this I2C about in 2 lines. So it's basically 2 lines to which the devices that are presented I2C interface are connected, and at every point there is a master-slave relationship between them. So where we start? So first of all, you have to decide what are your verification concerns for the design you pick, and what needs to be verified. So for this, you have to rely on specifications. And in our case, we had two papers. One was the design specification, and one was the I2C spec, from which we derived a verification plan that you can see on the right side of the slide. Mainly, it is covering all the functionality presented in the design, so it does not cover only the I2C protocol. So this is an end-to-end verification. And the goal was to verify each part, each bullet in this verification plan. And what is the first step that you take? So first of all, you do a quick analysis on your design. And you end up with some results, getting like how many states your design have, how many FSMs, multipliers, adders, and so on. In our case, it was a relatively simple design that presented I2C master functionality only. And we did an early automatic inspection. Why we did that? And we did that in order to get rid of early failures at an early stage. So, like signal domain violation, that code, unreachable FSM states, signal toggling. So we ran the auto inspection, we got the results, some of them failed, like initialization and so on. We validated the results and we move on. So now I'm going to talk about the approach we took while verifying the design. And this involves two components. One is the verification plan and one is the coverage tool. So first step I presented earlier was like the design. We run the inspection, early inspection, and next stage was to start writing assertions in order to cover bullets in your verification plan. And while you're writing checks to verify bullets in your verification plan, you same time tick items in the verification plan, and when you have, you can do that on a daily basis or weekly basis. When you have some results, by results you have some checks that are proven for a bullet in your verification plan, you run the coverage tool on top of it, on top of the assertions you have. And in this manner, so you do a bug hunting, and also you get the sense of how much your checks cover in your design. The next phase will be something like completing the verification plan. It involves same two components, the verification plan and the coverage tool. And I agree that these two phases are overlapping. So when you are writing assertions for bug hunting, you also complete bullets in your verification plan. So these two phases overlap. Once you complete your verification plan, you still can have big coverage holes in your design. And you analyze the coverage holes. What is the reason why you have coverage holes? And on top of it, you wrote the assertions to cover this. And on top of it, you run the quantify in order to see if you covered the holes. And at the end of the day, so you have, after you fixed all coverage holes, you still need to do a review over your assertions, constraints you have written for the design. And this can, and when it's once you reviewed, and maybe you did apply some modifications to the checks you have, you run quantify on top of it in order to see if you did not alter the coverage result. So mainly, this was the flow that we followed while doing this case study. So yeah, it is good to have a well-defined flow from the beginning. So what was achieved? So yeah, we started this case study in September, and we started to verify the design, wrote assertions on a, let's say, daily basis, and we got results. I'm not going to present all the results like day by day, so I got like, I think 5 screenshots from the results from the dashboard quantify. So you see that on, for example, on 16th of September, I had like 45 statement coverage and 70 branch coverage. And this was the phase of bug hunting. So you start writing checks to verify the design and try to cover the bullets in your verification plan. And with the time, you can see that the coverage grows, the number of assertions also grows. And at the end of the day, we end up at this metric. So we got 99 on branches and 96 on statements. And here I want to present like how the overall verification process was running over time, the verification process overview over time. So we started in September, we had no results. We had, from the beginning, a verification plan, which is the blue trend. So we started from 100% uncovered verification plan. We had no assertions at the time, and with the time we started to write assertions and to cover verification plans. So yeah, you can see it. So the bars are the statement coverage at certain dates. And you see the phase bug hunting and computer verification plan. I put them separately, but they overlap. So at the end of the day, we end up at 99, as you saw in previous slide, 99 on branches, 96% covered on statements. And this gives you a nice overview over how the things were running over the time. So mainly, yeah, we reached like 33% of uncovered items in the verification plan. So mainly, we did not verify the 10-bit addressing of the I2C. And in this example, I want to show you because one of the simplest examples where quantify was helping a lot. So mainly, it's spotting over-constrained code. So according to the spec, it says that, for example, you cannot have a read and a write at the same time. And the command register, for example, in this design, could do them both. So mainly you constrain this behavior from the, and you cannot accept a read or write bit set, read or write bit set at the same time. So this was the manner you write it first time. And on the top of it, you run, and you have some checks, everything on the assertions were holding. But when you run quantify, you see that I cannot get to, I'm introducing some over-constrained code. And you start to investigate it. And then you come back to your assertion back, and you see that, hey, they cannot be, these two read and write cannot be set same time, but they can be left unset at the same time. And you modify your assumption. The coverage, the over-constrained code you introduce later is now covered. But this also points you to some point in which you have to think about, for example, yeah, but I can have a scenario that the start can follow a stop without transmitting any data. So this leads to this void message, which is an illegal format. Start immediate followed by stop in I2C, but yeah, most of the designs can handle it nowadays. Yeah, and this is the overall coverage. So it starts from it has over constraint, the statement covered, what's over time. And what I want to present here is like the coverage results over time over the effort. And by effort, I mean the assertion effort. So how many assertions were written and how many constraints were written. So mainly you can see that the trend of assertions is following the trend of the coverage. So the dark green one, over time. Yeah, I want to first summarize this part of what was the motivation. So first of all was to see how can coverage assist in your verification process. And second is how we deal with serial protocols in formal verification. And why does the approach counts a lot is because you have to have a well-defined verification approach when you start verifying design using formal. Why it is good to have coverage? Well, coverage increases confidence and helps easily to identify over-constrained code and not exercise code. And collecting regression data over time gives a clear view over time on where the effort is spent and how the things are progressing. Yeah, so Quantify is widely used and it is scalable and automated, so it's a push-button solution. You don't need to set up it in order to run and collect coverage results on the assertion set you have written. So these are some numbers. So for big designs, so for 253 assertions from a design that has 57K lines of code. Yeah. And this is a real example of how Quantify performs in the industry. Yeah, and I would like to hand over to Vladislav to cover the rest of the part.
So just go back one slide. Yeah, so just want to say that this paper by Infineon is available. And if you have any questions, we have someone from Infineon who can just ask them immediately. All right, so this is another customer case study which basically just sums up what I was talking about and what Nicolae was talking about our design. The use of reservation coverage to identify coverage holes, and we can also integrate coverage result with simulation coverage. This is at the moment limited to assertion result coverage, but we are looking into code coverage as well. Basically what we do is we help and work with our customers to be simulator agnostic and integrate with any simulator. So we are very open to a cooperation in that manner. And Quantify is used, as you can see here in the slide, for ISO 26262 projects. And OneSpin has just gone through a tube certification and evaluation of our development flow. So for now we have some other tools certified, but Quantify will be certified for safety as well very soon. And before we conclude, we would just like to do a little comparison of why we believe Quantify is a superior coverage tool. And we'll start by cone of influence. Everybody has heard about this. So cone of influence can identify big gaps quickly, and problem is it can give you false optimism, especially if you write your checks in such a way that everything is in the cone of influence. Then it can be very misleading. For us, this is the zero step of Quantify. Of course, we target our effort where it is necessary, so we do weave out something which is not in the cone of influence, but we do much more than that. So it's a good approach to quickly get rid of stuff you don't need to look at, but it definitely is not the end of your effort. Then next is proof core. Again, result depend on a selected proof engine. As opposed to call-no influence, this is actually pessimistic and depends on the proof you're using. You can abstract much more away and actually get less coverage than you really have. I'm going to talk about that in a minute. Then this is closest to what we have, I would say, mutation coverage. So its limitations are a high write time and one fault at a time. Because remember I mentioned we have a free variable which we inject and not just only one fault model, such as a stuck at 0, stuck at 1 or something like that. And also this approach is intrusive. It sometimes requires application of the RTL calls itself, which is not good. And limitation to single fault models can actually lead to vacuous assertions or dead code, which is not really dead. And the results are not really presentable, so you have to go through a lot of data, a lot of scripts, so you don't have a nice HTML overview. And then in the end we have what we talked about, so quantify with fast execution, so we can actually process multiple faults at once. And it's non-intrusive, it's done on the model, not the RTL. It's what we call a just right level of abstraction, and we focus on the actual observability of your checkers. And as you have seen, the HTML report, it can be meaningful and it can be tailored to different use, whether it's design, management, verification engineer. They all share the same view. So if we go a little bit into what I mentioned before, for example, call-no influence, you can see that, for example, assertion A covers the green, and assertion B covers the red cone there. So what can happen easily is that, let's say you have an example property like this. You want to say that if I write to an empty FIFO, and I don't do a read for a certain period of time, after I do my first read, the data I read is going to be the data I wrote in. If you have an inexperienced verification engineer, or if you're not really that savvy with system Verilog, you might want to add that, or the FIFO is not full or empty. And this actually results in COI giving you 100% coverage, because if you look at full and empty, everything in the design can influence full and empty. And you get false confidence, and again, if you're inexperienced, you might say, oh, job done, great. But quantify would actually give you just 20% coverage here. And unrelated to the last line, because the more you add to the right side of the assertion, the weaker the proof is. So let's say if we remove this statement about full and empty, we would actually get a failing assertion that we can then debug. So what we like to say is, don't trust the COIs, and we don't trust them because we think they're fishy. So and for proof core, as I said, again, it doesn't cover what the proof doesn't need, so the proof engines can abstract away a lot. They get pessimistic. And another limitation is that, what at least we know, that you don't get access to all the proof cores for all the time from certain tools. Right? So that's also not helping your verification. And since OneSpin has a heavy focus on safety in general, we basically have this comparison of the coverage techniques there. So COI and proof core are definitely disqualified for safety. Mutation coverage is qualified, but as we said, high runtime, one fault at a time. We have some metrics that were run on a design which took 2 months with some mutation coverage, and quantify took 10 days. If you think of it, 10 days is still a lot, but the results you get on the overall design, that's a significant piece of information that can make sure that what you have is safe. So in conclusion, just want to reiterate once more. So we were talking about designer bring up and using quantify right from the get-go to measure your verification effort. We can do reachability analysis, redundant code. We can handle designer asserts, so it's already good. If your designer is willing to put some inline assertions, you already get some verification metrics as soon as you get the design before you start writing these assertions yourself. And these metrics can indicate gaps. Quantify will tell you where you have checks missing, where you have over constraints. And what is very important to take, what I would like all of you to take out of this is it's a push button solution. It has good runtime considering what it actually delivers and what it does. It's very easy to read, as you saw in the HTML reports. Can't show you here, but you can actually mix and match and just go through the lines of whole code that are uncovered, or just select the deadlines and so on. So it's very easy to navigate, very easy to go to your designer maybe and show him, hey, these lines are for some reason dead or uncovered, or did you mean to implement it this way or that way? So it really helps the discussion that verification engineers have with designers all the time. And what I like to say, it helps us hate each other less. And it's actually a single metric which will give you structural plus functional coverage, which is not something that is usually available out there. So at this point, I would say we were right on the hour. We were a little bit faster, and so I talk fast. That's who I am. So this was supposed to last for another 15 minutes, but hey, that gives you more time to ask any questions should you have any.
I note you sort of didn't address two things that I'd like to ask about. The first one is the depth of the amount of checking you did. You presented this sort of as a turnkey push button, but does the user have to interact with the tool to say how deep do you want it to search to come up with the check, or the responses? And that's number one. I'll come back with two in a moment.
Okay, so the tool being a formal tool, when it proves the assertion to be proven, it has its own depth, right? So it proves fully for the entire state space when the assertion proves.
Does the user give it that depth?
No. So it does this alone. Should you have bounded results, then you could discuss whether you need to increase the steps of the provers to maybe get a conclusive result, or if you're okay with the bound which is already there. This is for some maybe more difficult designs, maybe bigger problems that the provers get. So we could include bounded results into this, but bounded results are your own responsibility. If you're fine with the bound, you're fine. If you're not fine with the bound, we have certain techniques which would allow the user to play with the provers, maybe increase some depth and try to spend more time into getting conclusive results. But we have internal heuristics that target the provers at the problem they get, but we do allow user intervention if necessary.
So the second question is, does your tool and method catch formal properties that are never exercised? So we've talked about code that isn't exercised, but what about a redundant property that doesn't need to be there, that can be cleaned out?
I don't see properties as redundant myself, right? So if the property is proven on the design, you're welcome to keep it. I'm not really sure what you mean by redundant properties.
So the one that makes the most sense is, what if you have an assumption that you didn't need? That would be, it's an assumption property as opposed to an assertion, but that's the one that makes the most sense of something you'd want to cull.
I see. So if you have an assumption that is not needed to quantify, would probably point you to overconstraining.
Thank you.
Did you want to?
Oh yes, sorry. The first question. I keep forgetting this stuff. Yeah, sorry.
Thanks for asking our first question.
Okay, so this maybe takes several iterations potentially, but we'll see how it goes.
That's good because our product owner just walked in at the right time. So if I can't answer, he can.
So the first question, I want to take you back a little bit to what you were saying about proof call and it being overly pessimistic. So do you believe that if you were to run proof call and if you were to run quantify, you would end up in a situation where quantify gives you 100% and says everything's good, but proof call is telling you some pieces of the design aren't verified? And if that's the case, then do you believe that quantify is reliable enough as opposed to proof call, and why do you think that's too pessimistic?
Okay, good shot. So quantify actually observes the behavior of your code. The proof call will deal with the stimuli needed and the part of design which is needed to prove the property, whereas we actually here measure the quality of the checkers. So if the checkers tell you that they're sensitive to a line of code and that the checkers would start failing if the line is different, I would put more trust and emphasis on that than on anything else.
Okay. So, yeah, I guess I'm just trying to, I think it's quite interesting, the stuff you talk about and the way it's presented and stuff. It sounds like there's a lot of things going on under the hood as well, though, because you mentioned, for example, cone of influence analysis, it's too coarse. I think everyone would agree that signing off on something like that, we miss a lot of things. But it seems like you guys maybe do that under the hood as well as part of what's happening here. So do you provide that kind of feedback and information to users as to how you found something to be outside of the scope?
We do provide feedback because that wasn't part of the presentation, but good point. So if a line of code is actually covered, if you do a mouse over in the HTML, it will actually display which actual check is proving this line of code.
Okay.
So you do get feedback of what is proven by what.
Great. And then one final one, this maybe, I don't even necessarily expect to have them as hand, but it was good to see some data on kind of the runtime for certain things here. Do you have kind of a rough runtime to prove all the properties versus runtime for quantify kind of?
You mean like, okay. So it's kind of difficult to say because it depends on the design.
Sure.
Right? But I mean, you probably realize that what we are doing under the hood is rerunning the properties of the altered model, right?
Yeah.
So obviously quantify is going to take more time than just the assertion proving. But we do have clever internal ways how not to do it one by one assignment change, but we change the model in several places and we can calculate what we could put in a single run.
Okay.
So it really highly depends on the design.
Thanks very much.
Welcome.